Lesson 51, resonating air columns. This is another one of my favorite lessons of physics 20, because as most of you know, probably, I have a music degree. And so I love music. And in lesson 51, we're going to discuss how instruments work. We use instruments to discuss resonating air columns. But let's just review quickly. In lesson 50, we learned about standing waves, and we talked about strings, so like a guitar string or a violin string, anything that has a fixed end. And anything that has a fixed end, we said the shortest standing wave that you can make with an object that has a fixed end is 1/2 of a wavelength. And then you can make it one full wavelength. And then you can make it, what was that? You can make it 1.5 wavelengths and so on. Then you can go to two wavelengths and so on. So that's with if it's fixed to both ends, but resonating air columns are not fixed to both ends. So let's take, for example, a flute. In a flute, you blow into the air hole, and here's the air hole of a flute. You blow into that, and what happens, and then it's open here. It's open there. So how do you get a resonating air column in something without a fixed end? Well, what happens, let's again revert. We talked about this and this. What are those? Those are nodes. And at nodes, you have complete destructive interference. So a crest of amplitude 1 meets a trough of amplitude 1, and they cancel each other out and become 0. What are these? Those are the antinodes. Antinodes. And the antinodes are where you have complete constructive interference. So a crest of 1 meets a crest of 1, and they create a crest of 2. Or a trough meets a trough, and they create a bigger trough. And where you have the constructive interference, as this pertains to sound, as in musical instruments, is where you're going to have sound. So if you at a node, you can have an absence of sound, and at an antinode, you are going to have a maximum amount of sound. And then you get all the levels in between where some of a node meets, some of a crest meets some of a trough, and they're not the same amplitude, and so they sort of cancel each other out, but don't quite. So you get levels in between. But for right now, the most important thing is at a node, you get complete destructive interference, and so there is no sound. At an antinode, you get complete constructive interference, and so there is a maximum amount of sound. So the question is for this flute. Oh, did I forget? Sorry, I'm stopping the video here. Yeah, I really want you to go, and before you continue, stop this video and go and watch this one. It says Waves and Sound 12, open and close air columns, or you can wait till the end of the lesson. This will just reinforce what I'm teaching here. This guy explains it really well. So that will help you. Back to my explanation right here. So the question is, in a flute, how to create a standing wave so that we get sound? And the answer is, you remember with a string, the reason that you have an antinode or a node right here, let's go blue, you have a node here because the wave comes over here and then it has to reflect, and then it actually inverts, and that's how you get that pattern with half a wavelength. So you have to have a node because it reflects perfectly. If you have a flute where you have here a fixed end, and then here you have open, what must you have at the fixed end? You must have a node. So this is going to be a node right here at the fixed end so that it can reflect. And what do you think you have to have at the open end here, where the sound comes out? You probably guessed it. You have to have an antinode, because an antinode means the presence of sound, whereas a node means the absence of sound. So you have to have, oh, that was a crude drawing, but you have to have an antinode so that you can hear sound. Because if you had, let's draw it smaller. So here's your flutes. Because if you had a node like that, like half a wave, there's my half a wavelength. Remember the fixed string, half a wavelength produces a sound. Fixed, fixed. But if you have this situation where this is fixed and this is open right here, you are going to create a node right here, and this is going to not give you any sound. So in other words, half a wavelength, this is half a wavelength over here, half a wavelength cannot exist in this situation, the situation where you're playing a flute. You can't have half a wavelength in there because it won't produce any sound. And there's a great lab that we do on this where you can really hear clearly where the nodes and the antinodes occur. So what's my solution? Well, here's one of my solutions. Why don't I take that flute and get my saw and just like that? Oh yeah. There's a solution. Now all of a sudden we have an antinode right here, and an antinode means that we have the maximum amount of sound. We have the maximum amount of constructive interference. So what have I done? Besides destroying a really good flute, but I have now created sound, and how much of a wavelength is here? Well, that was half, right? And I just cut it in half. So this is how much of a wavelength? You guessed it, it's a quarter. A quarter of a wavelength is the smallest wavelength that will produce sound, or will produce a standing wave or a resonating column if one end is closed and one end is open. And we call this actually a closed pipe, a closed air column, closed air column. So we call it closed because it's closed on this end. Let's extend that. So what's the next wavelength that will produce an antinode at the opening? So let's just, we already said if it's half a wavelength, then no dice. Oh, I wanted that red. No dice. So let's keep extending it. Go. Well, there we go. There's the next one. That creates an antinode right here. How much of a wavelength is that? And this one you gotta think carefully about this. Let's draw it out. Here we go. Quarter, half, 3/4. So the next sound occurs at 3/4 of a wavelength. And then you'll start to see the patterns. The next one is, if that's 1/4 and that's 3/4, what do you think the next one's going to be? You get the point. 1/4, 3/4, 5/4, 7/4, 9/4. That's the pattern for a closed air column. And a closed air column has one fixed end and one open end. All right, so that's for something like a flute. We'll discuss the trumpet really quickly, and then we'll stop this, and then I'll do the mathematics of this in a separate video, just so you have time to digest the enormity of what we're talking about here. Well, it's not really that enormous. It's cool. So that's for a flute. Other instruments, such as a trumpet or a clarinet, those are classified as open-ended columns because they're open at both ends. So they're not closed here. They're considered to be open. And for this to work, what do you have to have at both ends? We already said for the closed column, you have to have a node here and an antinode here. So for this one, clearly you need an antinode at both ends, there and there. And if you need an antinode at both ends, what's the shortest wavelength that will fit in there that will create a sound? So you have antinodes at both ends, and that would be, let's do it like this, actually. I'm just drawing that. That's I've got a node at one end and an antinode at the other end, and I'm just going to cut it down with my eraser until I achieve the shortest wavelength where there are antinodes at both ends. So here's the one thing I could do. There we go. I've got antinodes at both ends right there. But I can make it shorter because I can do this. Mission accomplished again. And that's going to produce a sound because it has antinodes at both ends. Can I make it any shorter to have antinodes at both ends? And the answer is yes. I can go. There we go. I know that doesn't look great, but that is the shortest wavelength. And how much of a wavelength is that? It's kind of difficult to see. Oh. Like the string, the shortest wavelength you can have for an open-ended air column is half a wavelength, which kind of makes sense because if the string is closed on both sides, you can have half a wavelength. If it's open on both sides, it's the same thing. You can have half a wavelength. It just looks different, right? It looks different like that. Yeah, that wasn't very good. You get the point, like that. There we go. That's half a wavelength. And then you can make it a full wavelength. I'm terrible at drawing these. There we go. Now that's a full wavelength. So half a wavelength works, one full wavelength works, and the pattern is the same as a closed or one with fixed ends, a column with fixed ends, a vibrating string. It's half a wavelength, one wavelength, 1.5 wavelengths, 2 wavelengths. I should write this as 2/2. 1/2, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves. So every time you go half wavelength longer, then you will create sound in an open-ended air column. Okay, so quickly in review, because it's a long lesson and I'm only halfway through. In review, if you have fixed or an open-ended air column, 1/2, 1, 1.5, 2, etc. If it's an closed pipe, then it's 1/4, 1/4, 3/4, 5/4, and so on. And the commonality between all of these is that each time to go from there to there and there to there, to go from there to there, there to there, you are adding half of a wavelength. All right, so that's the basics of it. Part 2, we'll discuss the mathematics of it.